Hello and welcome to this, our latest in a series of Building Line real-time webinars. My name is Denis Gray. I'm the Product Manager for Building Line at Mapei, Australia. And I'd like to welcome you and thank you for your attendance this afternoon. I hope you enjoy the topic, which is elastic sealants and chemical anchors in construction. Okay, I hope this finds you all well and that the COVID pandemic hasn't been affecting you too much. Sit back, relax, and enjoy the presentation. Please stay online after the presentation if you have any questions, or you can at any time email me on d.gray@mapei.com.au if you have any questions after that. Okay, so without any further ado, we'll get started. Okay, so when we talk about elastic sealants, elastomeric chemical products that form tightly sealed joints and seal cracks and crevices, preventing air, water, dust and foreign bodies from entering or exiting, even when subjected to deformation. A good joint sealant must be able to overcome several different deformation forms. This can be tensile and compressive with expansion and contraction of joints. It can be shear loads or flexural or torsional loads, as seen in the diagrams here. Joints are breaks which external agents can penetrate. So elastic joint sealants guarantee the joints the necessary air tightness and deformability over time. So elastic joint sealants have an almost irrelevant effect on the total cost of a building. However, they do have a huge impact on the building envelope efficiency if not done correctly, and certainly consequential damages can also occur. There's a lot of different products that come under the heading of elastic sealants in construction. And there's also a significant amount of different chemical natures. They can be acrylics, they can be acid cure silicons, neutral cure silicons, they can be hybrid materials, single component polyurethanes, two component polyurethanes, epoxy polyurethanes, they can be polysulfides, or they can be butyl based, or even bituminous. So there's a numerous amount of different chemicals that come under the heading of, or that can be used as sealants. When we talk about sealants and their cross-linking or curing process, there's also a lot of different ways in which they cure. So they can be a solvent evaporation, it can be a water evaporation or loss of moisture, it can be a reaction with the environmental or the humidity in the air, or in the case of two-component materials, a reaction with a special hardener that's mixed at the time of application. If we look here at the two diagrams, in the top section, we look at single component materials, and they generally tend to cure from the outside in. So the area exposed to the air or where the release of solvent or water can occur, and gradually migrate through to the point where it's fully cured. In a dual component material, this tends to migrate from a plastic state or an uncured state, starts to gel, gets thicker, and eventually fully cures. So there's two different types of actions taking place here. When we look at one component sealants, also need to be very careful about the actual timing and how quickly they do cure. In the first 24 hours, they can seem to cure quite quickly. Some materials will cure up to 3 or 4 millimeters in the first 24 hours, but then only another 2 millimeters in the subsequent 24 hours, and maybe another millimeter in the 24 hours after that. So if we look at the diagram on the side here, on the left, we have from initial application, 3 millimeters in the first day, 5 millimeters in the second, 6.5 in the third. By the 5th day, it's 7.5 millimeters and 9.5 after 10 days. So sometimes people tend to apply a large amount of joint sealant and expect that once it's skinned, that the rest of it will also be cured. This is not the case. Okay, when we start to talk about the different chemistries, there's the acidic cure or acetoxy silicons, which have a lot of good points, but also have some negative aspects. So easy extrusion and workability, excellent adhesion to glass, ceramics and non-porous surfaces, chemical resistance, heat resistance, generally up to 150 or 180 degrees, and in some cases much more. Their elastic behaviour, they're capable of being transparent or clear, and are, generally speaking, very low cost. The cons or the downsides, acid reactions incompatible with mineral substrates, it's corrosive incompatibility with oxidizing metals, so you can't put it onto base metals. The smell emitted, the vinegary or the acidic smell, the ease of qualitative cutting, so these materials tend to be quite low in tear resistance, and they're often the lower end or poor quality, and certainly, as is the case with most silicons, not paintable. When we look at neutral cure silicons, again, the pros, easy extrusion and workability, compatibility with many building substrates, their elastic behaviour, chemical resistance, heat resistance, and again can be transparent. The cons, again, low tear and indentation resistance, so they tend to be soft and not so strong a backbone. The stain of natural stone surfaces, migration of plasticizers can occur, and this is the case with both acidic cure and with neutral cure materials. On natural stone, the migration of plasticizers and silicon oils can significantly damage the surface. And of course, again, neutral cure silicons are not paintable. We move on to the one component polyurethanes. Multiple substrate compatibility. Elastic behavior is very, very good. They can be painted. They have very high tear strength. They have high adhesion, excellent on non-porous surfaces, formulation of flexibilities from high modulus to low modulus. I'll talk about that a little bit more later. And the cons, I guess, are the extrusion difficulties at low temperatures. They tend to be a little harder to gun than silicons. The surface aging by UV over time. They tend to get oxidation and crazing on the surface when exposed to UV. We look at maybe a newer technology, been around for a while now, but still one of the newer ones. Modified silicons, silylated polymers, MS polymers, these hybrid type materials have certainly had a great following. So multiple substrate compatibility, they bond to most substrates. Their compatibility with wet substrates during installation is a big plus. They can be applied on damp surfaces. Elastic behavior, they can be painted. They're also crystalline transparency, so they can be a crystal clear material. They're limited dirt retention, so they don't tend to attract or hold dirt. And the formulation can also be a high modulus right through to a low modulus material. And modulus, by that I mean it's the force required to deform the material. So a low modulus material tends to be much more elastic and flexible, easy to stretch or deform, whereas a high modulus tends to be a little bit more firmer and a harder material and takes more force to deform. So the cons of a MS polymer are quite few. There's only really the low tear resistance. So it's one of the points that it's taken from, I guess, the silicon side. Two component materials. Not that many around nowadays, but the multiple substrate compatibility, they're high resistance to chemicals, high adhesion and high elasticity. The cons are that they're two component and they need to be mixed. There is potential mixing errors on sites. You have a wastage of surplus material when the job's completed. Mix a kit and only use some of it. You can't put it back in the bucket because the two components will react. So Now that we know a little bit about the different types of sealants, there's also the technical certifications, and there's a lot of different ones throughout the world. The American standard's very common. The German standard, the DIN, the ISO, the Japanese standards, the CE marks. All of these are widely used in the sealant arena. So they have been harmonised, the standards, and the European standard is also one that is widely looked at or understood here in Australia as well. And when I was talking earlier about low modulus and high modulus, in this graph here, you'll see there's sealants for facades, sealants for glazing, sealants for sanitary areas, and also sealants for pedestrian and walkways, so more trafficable type areas. And when we look at the gradings down the side, we look at 25 LM and MAF, so that's a plus or minus 25% low modulus or low elastic modulus, and the movement accommodation factor, which is MAF, is plus or minus 25%. Now this is 25% of the actual joint size in movement. So we move on now to the application of joint sealants, and the application is quite simple, yet there's quite a structure required. You need to understand the surfaces that you're dealing with, what you're actually applying the sealant onto, whether it's cementitious, so concrete, mortar, prefabricated blocks, bituminous conglomerate, bricks, stone, wood, or whether they're non-absorbent substrates like metal, glass, ceramic, rubber, plastic, paint. All of these sort of things are needed to understand before you set about doing a joint sealing application. So once that's been understood, you take the substrates, if required, apply a primer, and then this thing called a backing rod. So I'll talk a little bit more about this because it's quite important. So once the backing rod's in place, then we apply the sealant and everything's fine. The problem is backing rods don't necessarily get used correctly. When we go on and talk about primers, backing rods and the sealant application, the primers really need to be understood as to why and where you would use one. And the three main areas where you would use is physical preparation of the substrate by coating the continuities and irregularities of the joint edges, sealing porosity to prevent bubbles from outgassing, or chemical preparation of the substrate in the case of, say, plastics or the like. There's a whole range of different primers that work very well with different sealing compounds. I won't go through all of those, but the data sheets on all of the products tend to give a good indication of how much or which types of primers should be used with which substrates. And it should also be noted that the primer is more substrate specific than the actual sealant. Okay, so we were talking about backing rods before, and I said it was quite an important point. So a backing rod is there for two reasons. One is to ensure the width to depth ratio is correct, and the other one is to ensure that you don't waste material, you don't use more than what's required. So in a case of a joint up to 10 millimeters, the width to depth ratio is 1 to 1. And then once you go wider than that, as you'll see in the graph coming up on the next slide, it moves to 2 to 1. What we often see and where failures occur is when the incorrect positioning of a backing rod, or in fact, someone thinks they're doing the right thing, but totally filling the joint and getting adhesion to all three sides. This is the other area where a backing rod comes in very handy. It ensures that you only get adhesion to the walls, to the two sides of the joint, but not to the base. By having adhesion to all three sides, you reduce the movement capability or capacity of the sealant quite significantly. Okay, this is a graph I was talking about. So we talk about width to depth ratios. Up to 10 millimeters is 1 to 1. From 15 to 20, it's generally still 1 to 1 or 10 mil deep, and the width. And then from 20 mil on is 2 to 1. So 20 mil wide, 10 mil deep, 25, 12, 30, 15. So this rule of 1 to 1 up to 10 millimeters and 2 to 1 width to depth ratio over that is a very hard and fast application criteria. On the diagram to the side here on the left, you see the chamfered edges on the joints. Now, if you have a trafficable area or where there's people walking across it, vehicles, maybe machinery and the like, it's always prudent to chamfer the edges, because this section at the top here is generally weak and friable and will break away. If you remove that and set the joint sealant down, two things happen. You remove that weak and friable edge, and you also set the joint sealant down below the trafficable area, so it tends to get less wear or effect on it. Okay, so let's start to talk about maybe an application. So the most important thing is to clean the surface. By doing no cleaning regime at all, you have no idea what contaminants are on the surface. So always, at very least, give it a light wipe and remove any dust or contaminants. Then apply a masking tape, so protection of the edges to the joint and where you want to finish the joint sealant. We'll then talk about a backing rod, or in the case of no need for a backing rod, perhaps a bond breaker tape, so just a cellophane tape that prevents adhesion to the base of the joint as well. And then, of course, the extrusion of the sealant into the joint. And from there, tooling it off efficiently. Now, tooling is also an art form, and generally speaking, if any advice could be given, I would say the quicker and more even the tooling process, the better the finish will be. Also, very handy to remember, remove the masking tape while the sealant is still wet. It becomes very hard to remove once the sealant has started drying. Okay, so once the curing or the polymerization has occurred, then the sealant can be put back into service. It's very important to also understand that as simple a process as a sealing application can be, there's also lots of times where it doesn't quite go right. And you see some pictures here of sealant defects and lateral delamination of the sealant. Now, this is a very, very common thing to see, where you'll have a debonding from one side, it will hop across to the other side, debond back and forth all the way down a joint. And this is not uncommon. And the main causes for that are the elasticity of the sealant insufficient to absorb the movement. So maybe the wrong sealant was used. The sealant has inadequate depth to width ratio. We talked about having a backing rod or making sure that the width to depth ratio is correct. And also the sealant may have adhered to the joint bottom, so not having a bond breaker. And the solutions here to avoid this from happening is to use a sealant with adequate elasticity, of course, correct dimensions of the width to depth of the sealant, and place a specific non-stick backing rod in the bottom of the joint. Will go a long way to avoiding this occurrence. Okay, we'll look at failures of adhesive sealants. The sealant hasn't adhered to the joint edge. It's in showing this diagram here. It's just totally debonded. And it can be a number of things, but the most common is the substrate was dirty, was never actually cleaned before, so the preparation wasn't correct, or the substrate wasn't compatible with the adhesive, so it wasn't going to bond. And I see this a lot with joint sealants where a panel may be painted before the joint sealant goes in, and the joint sealant goes in onto an acrylic paint that's been out in the weather for a little while, and of course it doesn't bond because it's not a structural surface or a structural substrate to bond to. So the solution there is properly clean, make sure you degrease, remove any curing compounds, waxes, or oils and things like that, and also to use a specific adhesive primer for the substrate to increase the adhesion and the longevity of the adhesion of the sealant in the joint. Another one that you see quite often is cracking along the center of the sealant. And this is not an uncommon thing. This looks like it also has a few other problems, but the sealant cracks in the center path or the center part of the joint. And the possible reasons for this is the elasticity of the sealant isn't sufficient to absorb the movement of the joint. But in that case, the adhesion to the substrate on either side is sufficient or is better than the actual cohesive strength of the material. So it tears within itself instead of pulling away from the substrate. The sealant also may have underwent a volume shrinkage. So some sealants can have quite significant shrinkage, can be up to 10, 15, maybe even 20% in some cases. So it immediately puts the joint into a dumbbelling or a tension force from the outset, and that tends to rapidly deteriorate the bond over time. So the solution here is to use a sealant with adequate elasticity to absorb the movement of the joint, and also to use a sealant without volumetric shrinkage. Okay, another problem you see, and this one's more substrate related, but the joint edge cracks or peels. So before a joint sealant is applied, it should also be checked to ensure that the substrate is suitable and it's not going to break up and fall away, as you see in pictures here. So the possible reasons, of course, is the sealant's too rigid and stresses the joint edge, detaching it, or the joint edge is mechanically weak, as I said. How you can avoid this is to use a sealant with a higher elasticity. So in that case, it would be a low modulus material. And the other option is to restore the edge with an appropriate technique before rejoint sealing. Okay, this is an interesting one, and not everybody finds this out the easy way. They sometimes find it out the hard way. So staining of substrates, it is a real problem. Generally on porous substrates and natural stone, the joint edges become impregnated or permanently stained. And the possible causes of that is the hardened sealant releases plasticizers that migrate into the substrate, staining it. This is quite common with silicons. It rarely happens with polyurethanes or MS polymers, silylated polymers, and any of the hybrid type materials. But certainly in silicons, where they can naturally bleed silicon oils and plasticizers for a period of time afterwards, this is quite a real problem. You also see it on buildings with large natural stone facades, and throughout Asia, this is prevalent. There's cheap bleeding silicons or cheap silicons being used to joint seal against natural stone, and it migrates the oil into it, and it's irreversible. That's totally ruined. It can never be cleaned off or removed. So the solution is to use a stain-resistant or a non-staining material, and that can be Mapei LM, which is one of our silicons, but it's a unique silicon in that it does not bleed silicon oils and will not stain natural stone. Alternative to that is one of the MS products or the polyurethane, the Mapei PU range. Another problem you see is dirt or dirt pickup And this is atmospheric dust settling on the sealant. It generally accumulates and dirties the sealant and the adjacent surfaces and makes it look very unsightly. The possible causes of that is the high electrostatic charge, which attracts and retains that atmospheric dirt and just basically sits there. So when it rains, it bleeds down the side of the building as well, looking very unsightly. And the solution for that is to use a low electrostatic charge type material, and that can be a Mapei MS, so an MS polymer, or a polyurethane type product. So it's important to not only understand it may be doing a perfect job in the sealing function, but aesthetically or the damage that it can be causing to other components can be irreversible. Discoloration of sealants is also quite a common thing. Atmospheric dust settles on the sealant. Sometimes it's while it's still wet, so it's almost unavoidable because unless it's protected while the application occurs. But this can also be electrostatic charge, which attracts and retains the atmospheric dust. So again, in these cases, good protection and closing the work area off and ensuring that no dust blows in, but also using a low or a no electrostatic charge type material like an MS polymer or a polyurethane. Okay, don't want to dwell too much on problems, but there's quite a few of interest that really need to be talked about. Painting over sealants can also be an issue. Paint can be applied and start to peel or crack. And the possible reasons or causes for this, it's a non-paintable sealant that's been used, so silicone, or the paint used isn't sufficiently elastic to accommodate the movement of the joint. So in all cases, when painting over a joint sealant, the elastomeric properties of the paint should be equal to that of the actual sealant. Okay, softening of the sealant. This is generally an issue that is chemical related. So it softens partially or totally loses its elastic characteristics. It may become sticky, or it may turn totally back into a plastic state. The sealant undergoes a prolonged chemical attack is the most likely cause. The use of a high chemical resistant sealant can avoid this, but also regular housekeeping to remove any spills or contamination sitting on a joint sealant for too long. So housekeeping is a big part of this as well. Okay, in the bathroom, in wet areas, mold formation is something that everybody's seen over the years. So the surface or deep spores of mold go into the sealant. Perfect scenario is a high humidity, higher temperature type application. Where moisture sits for a period of time, it's a perfect scenario for mold to grow. Possible causes, the sealant doesn't have a biocide in it or not sufficient biocide, or the bacterial stresses are particularly high and continuous. They can still grow on the surface, but the solution is usually to use a suitable biocide added material, adopt a systematic and adequate cleaning and ventilation of the rooms, so good housekeeping, and also to use a good quality material that has the biocides in it. Mapei AC and Mapei LM are those. Okay, here's an interesting one. The joint is not sealed at all. So when there's no joint sealant, there's contamination, all sorts of things that can occur. So the causes for this are generally gaps in the design that have not been considered. It's an incomplete installation. And as I said, yet not considered a potential issue at the time, but it's quite common to see, particularly on roadsides, where trees and weeds grow out of gaps in the concrete. And I've seen cases where fig trees and things like that actually grow and cause some significant damage to infrastructure and road networks. So sealing keeps the or avoids any growth occurring. Okay, so the range of Mapei elastic sealants and sealants in general is quite wide. So there's obviously different polymers, as I explained. There's single and two component products. There's different elasticities and different hardnesses, different cure speeds. Certainly there's different chemical and temperature resistances. So in Australia, we summarise the product range available at Mapei as all single component adhesives and sealants. And I'll talk a little bit later about one and two component adhesives in the anchoring side of things. But all of our sealants, flexible adhesive sealants, are single component, no mixing required. So just running through those, we look at acetic cure, so Mapei AC. It's a ceramic bathroom and kitchen material or silicon, 34 colours. It's a pure silicon, so it doesn't have fillers in it. It's solvent-free. It resists mould. It has mould inhibitors in it. Low elastic modulus, and it's a premium quality material, as you would expect from Mapei. The Mapei LM is a natural stone facades material. So this is a non-bleed silicon that is safe to use on natural stones. It resists mould, comes in 10 colours, and again, it's also low elastic modulus, so it can be used in joints with moderate movement capability or requirements. We move from the silicons onto the polyurethanes, and these single component polyurethanes, Mapei PU40, it's a high movement joint and crack sealing material, low modulus, it's paintable, swell free, there's no bubbles, and it's easy to extrude. The Mapei PU45 FT for fast track, is a fast setting. This is a little bit different here. We start talking about adhesive sealants. So this is a multifunctional material. It can be used for sealing, so it's an excellent sealant, and I'd say an excellent adhesive as well. So flexible adhesive for bonding dissimilar materials, or the same, that allows for some movement because of its flexibility. It's also paintable, swell free, and this one's a more high modulus, so a stiffer consistency material. Okay, we move on to now the hybrid materials. So Mapei MS45, multifunction, again, it's an adhesive sealant, excellent sealant and adhesive properties. It's paintable, even for wet substrates. So these the MS products, particularly MS45 and MS Crystal, they can be applied even on damp substrates and get good adhesion. So it's a unique characteristic of this product. They have high elastic modulus, and they're also quite easy to extrude. Interestingly, it also comes in a crystal clear version, so it's almost invisible when applied on a mirror or between glass and those sorts of things. So again, very multifunctional and a highly elastic modulus material. There's a range of guns to apply the materials. These are necessary accessories that are used for the application of the joint sealants. And talking about the sealing solutions, the elastic sealants are used in every construction detail, both in new buildings and also in the renovation of existing ones. They're simple and easy to use, and they're all single components, so there's no mixing required, no wastage. They have different cure times, they have different elasticities, and it's often possible to use a number of different Mapei products to solve the same solution. It's a matter of looking at all of the benefits of each of the different products, whether you want a fast cure or a slow cure, and picking the one that suits your application best. Excuse me. The common needs are solved with best sealing solutions. So when we talk about the solutions, in particular for water retaining or drinking water type tanks, MS45, the Mapei single component hybrid sealant. It's applicable on wet surfaces. It's good hardness, good elasticity. It's a thixotropic or slump resistant material, and it's suitable for continuous contact with water, including drinking water. And I asterisk this because it still needs to be tested to the AS 4020 2018 standard. So at this stage, it's not approved in Australia for drinking water, although throughout the world it already has that certification. Low certified environmental emission, so low VOCs, and again, it's paintable. We look at PU45FT. I said before that the polyurethanes have very good tear resistance and are more robust. So being fast curing with no bubbles, most suitable for high traffic resistance, easy to apply, have very good adhesion, and again, can also be painted. We'll look at the silicons. Mapei AC, pure acidic cure silicon with low elastic modulus, perfect for swimming pools, both in and around the swimming pool, and all wet areas because of its mold resistance. The LM, talked earlier about the non-staining. Again, this one is a neutral cure. It's certified for use on all stones. It has high durability, resistance to mold. It comes in a range of colours also. Another area where Mapei AC is used is just any ceramic tiling type application, indoors or out. Being a pure silicon, has superior strength and durability, prolonged resistance to mold, and it comes in 35 different colours. 34, I think that is actually. Low elastic modulus and a high thermal and chemical resistance. When you look at additional cracks and crevices and the like, this is where PU45FT and even PU40 for that matter can be used. They're both fast curing, they don't produce bubbles, very good high traffic resistance, ease of application and high adhesion to the surface, and are paintable. PU40 is particularly suitable for tilt up and precast elements, joint sealing between. It's easy to apply, has high adhesion, and again is also paintable. The new products, the MS45 and the MS Crystal, are also bubble free. They're high elasticity. They're excellent adhesion to even damp substrates. And the ease of application and the high adhesion make them very suitable for connection joints around windows that are often painted afterwards. So when we talk about paintable external sealing applications, we have a number of products that are suitable for that. Certainly the silicons cannot be used because silicons aren't paintable, but the polyurethanes, particularly the PU45FT because of its fast cure, and the Mapei MS45 and MS Crystal can be painted over very quickly and makes it suitable for lots of, I guess, time restraints on construction sites. Okay, we'll quickly move on to chemical anchors in construction. It's an interesting one. It's basically a comparison between mechanical fasteners and chemical fasteners. So the anchorage systems are made up of both, or several components. So there's the substrate that they're fastened into, the actual fastener or the chemical anchor, and also the fixed element. So the overall performance of the system must ensure that the anchor remains solid when exposed to external forces. Here you'll see like a dynabolt scenario, and here is a chemical anchor adhesive. So when you talk about mechanical fasteners, their operation is by friction onto the masonry or the concrete. The main areas are very widespread, and it's an instantaneous operation. So with these mechanical fasteners, you get an instant result, and you don't need to wait for anything to cure, so it's immediate. Its concentrated stress distribution is a problem. and there's a high separation between fastener, and of course corrosion can be a problem with these metals. When you look at chemical anchors, by adhesion, the pros, there's no mess when laying, the homogeneous distribution of stress, which you'll see shortly, suitable for any diameter and anchoring depth, and it reduces the distance between anchors required, electrical insulation, and also anti-corrosive protection of the actual anchor. So it's encased in a protective material. I guess the cons, operation only after a few hours, so it takes time for the curing to occur, and also compliance with the laying procedures. So, okay, so we talk about the characteristics of mechanical fasteners. Here we have a mechanical fastener and the force trying to pull out. So we have this stress or load build-up. When the stress, they stress the substrate already during installation. So they're immediately under stress. They require the development of an expansive force, and the expansive force is concentrated on the bottom and not all the way through the anchor. So it's not distributed along the whole perforation. The high edge distance and the high inter-axis distance is also an issue. When we talk about chemical anchors, they don't stress the substrate. During installation, they require the development of an adhesive force, so the bond of the anchor holding it against the walls of the hole, and the adhesive force is homogeneously distributed along the whole perforation. So there's a limited edge distance, there's limited inter-axis distance occurring here. So to make that all quite plain and easy to see, the mechanical fastener transmits high and concentrated stresses to the substrate, and the chemical anchor transfers limited and distributed stresses quite evenly. So as I said before, the mechanical fastener has all of the load in one area, whereas the chemical anchor evenly distributes the load across the whole surface area of the hole. So when we talk about certifications, structural products and materials for the construction industry must be identified and qualified in order to be used in projects and construction sites. In Australia, we have AS 5216 2018, and it is in harmony with the European standards for chemical and mechanical post-anchoring as well. So several ETA, this is the European testing certifications available depending on the field of application, and they're most commonly the ETA option 1, which is for cracked concrete, and the ETA option 7, which is in the non-cracked concrete zones. To make that easier to understand, we have here compressed zone, the non-cracked zone in a concrete element, and on the underside we have the cracked concrete. It doesn't necessarily mean there is cracks, there's a potential for. They're also totally suitable for fixed threaded rods and also for fixed bars with improved bonding, so reinforcement rods. Okay, there's also a lot of different chemicals that are used or chemistries that are used in anchoring. There's polyester resins, there's vinyl ester resins, methacrylic epoxy acrylate resins, urethane methacrylate resins, and epoxy resins, generally speaking. So the polyester resin, being the cheapest and probably most widely used as a general purpose material, is low cost, fast curing, it's compatible with masonry and stones, and it's compatible with wet or damp substrates. Some formulations aren't. The cons, it's noticeable volumetric shrinkage. We'll talk about this a bit later. Not suitable for cord holes, and it's not suitable for permanently damp or wet anchors. Another con is reduced number of certified diameters that can be used. When we talk about the hybrid or the vinyl ester, it's certainly a much faster curing as well. compatibility with all common building materials. It's a very good general material that can be used in regulated and unregulated markets. It's compatible with dry substrates. The VESF, which is the vinyl ester, solvent-free or styrene-free, can also be used in flooded substrates, and there's a wide flexibility of use. So the cons are generally not suitable for cored holes, and there's a risk of staining on stone. We move to the epoxies, the 100% solids epoxy, prolonged workability, ideal for hot climates because they have nice open time, compatible with all the common building materials, compatible with dry, damp, wet, flooded substrates. They can be used underwater. They're also compatible with cored holes. There is no shrinkage whatsoever with the 100% solids epoxies, and subsequently they can be used in all these applications. The cons, I guess, are that they're a higher cost and the reaction time is much slower in the curing. Okay, again, there's a number of accessories, guns, static mixing nozzles, and perforated sleeves that are available for hollow sections, but also for the application of the materials. It's important to ensure that the right mixer is used. Always check the correct sizing of the anchor according to the design choices. Mapei has a design software. It's available for architects, engineers, and designers. It can be downloaded from our website. There's numerous design variables. It can be fixings into tense or compressed areas, fixing into seismic areas, different qualities and conditions of the substrate, different qualities of the metal bars, and also different ways of drilling the holes. That can be either coarse or diamond cored. It allows the control of each intermediate step of the calculation, and transparent sharing of the calculation criteria can be adopted. Okay, the selection criteria. The choice of chemical anchor is influenced by many variables. It can be the project variables, or it can be product characteristics. Project variables, natural and condition of this nature and condition of the substrate, it can be the hole positioning, the perforation method, the type of extent of the load, and also the environmental operating conditions. Variables of the product, of course, setting and hardening times, post-hardening volumetric shrinkage. As I said before, the polyester resin has some shrinkage. Vinyl ester has also a little, but the 100% solids epoxies have no shrinkage. Fire resistance may be an issue, and also the cost. So between these, we'll come up with the ideal chemical anchor for the application. They're used both in new and in renovation of existing buildings. The Mapei range of chemical anchors meets all of the job site needs, always guaranteeing safety and reliability. The structural and non-structural applications, anchors and cold joints can be used. Uses for static, dynamic, and seismic loads. So it's all of the applications, and we have all of the certification to go with that. Products are always certified. We have selected the most common anchoring needs and identifying our best fixing solutions, and they are this. So the Mapei Fix PESF is a styrene-free polyester resin for anchors in non-cracked zones. So as I said before, we have the ETA certifications, but it is a general purpose for more the less critical type applications. We go to the vinyl ester resin, or the hybrid material, and it has more qualifications, certifications for anchors, even in seismic applications. It has fire resistant certification, can be used in flooded holes, and for static and dynamic loads. So it's a great flexibility of use. This one is the real all-rounder. From there, we move to the Mapei Fix EP385, and it is 100% solids epoxy. Sorry, that is the wrong drawing there. And it has the most certifications. So this EP385, the 100% solids epoxy, is the top of the range as far as anchors go. So it can be used across the board in all applications. So Moving forward, resources-wise, Mapei has a wonderful website with a lot of information, all of the technical data sheets, the safety data sheets, relevant information, including project references from the world over. So have a look at our website. There's lots of wonderful information that you can source there. There's also the Mapei app that you can get for your smartphones and for your smart devices, both the Apple and Android applications, and that can be easily downloaded from the App Store or Google Play. And there's also a whole range of different brochures that can be used as a point of sale, but also just as a general overview of the different products. So these are also easily obtainable from your retailer and at the point of sale. So that brings us to the end of the webinar today. I certainly hope you've enjoyed the presentation. Please stay on the line, and if you do have any questions, I'd love to answer them for you or endeavour to answer them. Otherwise, if you do at some stage after this have a question, by all means email me, d.gray@mapei.com.au, and I'll be more than happy to assist wherever I can. Thank you. I appreciate your time today, and I hope you enjoyed and got something out of the presentation. Thank you. Thank you, John. So if you do have any questions, just please type them in and I'll answer them for you. But again, if you can't think of any right now, any time that suits you, by all means email me or give me a call, and I'll be more than happy to assist or answer any questions you may have. No more questions? Okay.